Welcome back. We were discussing about the properties of the Fourier transform. So, last video we have done certain properties. Today we will do some more properties, some very important properties on convolution products. We define what is convolution product, and Fourier transform of it is a product of the Fourier transforms. And we see some important equality, it is called Parseval equality. These things along with Riemann-Lebesgue lemma, and then eventually we will try to solve, we will try to prove Fourier integral theorem, which is the backbone of this Fourier transform. So, through which we have defined this Fourier transform. Okay. So, let us do some more properties. So, another important thing is ninth property, let us say if it is 8, it is 9. Property 9 is if I define, so let me define what is a definition of convolution of two functions. If let f and g, f of x and g of x be two absolutely integrable functions. Absolutely integral functions in minus infinity to infinity, then f star of g, this is the convolution product of this, which is a function of x, as you define it as the integration over a product of these functions in such a way that you can define f of x minus y into g of y dy, which is function of x. So, this is how if you define, you can see exactly. So, we will try to define in such a way that so we may have to add some constant if required. So, that we will see this is the definition of this convolution product is this. So, now the property tells you that if f and g are two absolutely integrable functions, if f and g, f of x and g of x are two absolutely integrable functions in minus infinity to infinity, then what you have is you take the Fourier transform of this function convolution product, which is a function of xi, will become Fourier transform of that and Fourier transform of g. Okay. So, you may get something like root 2 pi, so that you get a good identity. Why we add this? So, I think this is what we have. Okay. So, this you can adjust by redefining your convolution product. You can remove this depending on. Okay. So, let us prove this one. So, we use this way. So, let us define this, and then we will get this one. If we do not get this, that means we will have to redefine. Okay. So, let us see what we get. Is this really true? We will see. Okay. So, what you have to do is you take this LHS, that is f star g of x, for which you take the cap Fourier transform. By definition, this is 1 by root 2 pi minus infinity infinity f star g of x into e power minus I xi x dx. Xi belongs to real numbers. This is the thing. So, what you get is now 2 pi. Now, you write this exactly what this definition of convolution product, and what you get is minus infinity infinity f of x minus y g of y dy into e power minus I xi x dx. So, because f and g are two absolutely integrable functions, and you can see that this is minus infinity infinity of this whole thing f of x minus y g of y e power minus I xi x dy and dx. This is less than or equal to minus infinity infinity minus infinity infinity f of x y x minus y into modulus of g of y dy dx. So, this because f and g are two absolutely integrable functions, f of x minus y is also absolutely integrable function, and then also g of y is also this product, as you can see this product is also absolutely integrable function. You can say this is a product of g, this product is also absolutely integrable function. So, because this is that means this is finite, that is the meaning. So, because of this there is something called Fubini's theorem. You can just have a statement, this is very useful and important. If f and g are two absolutely integrable functions, if f x and g x are absolutely integrable functions, on any domain. So, you can take finite interval or any subset of real numbers, or you can take the full real number set. So, let us use the full real numbers, that is functions in minus infinity infinity. Then and what you have is this double integral minus infinity to infinity minus infinity to infinity. This is double integral of f x into g x. So, let us say g y, let us say g of y, okay. F x g y dx dy, if this is finite, okay, this product, this if this is finite, then that is exactly what we have, okay. So, then if this is the case, f x minus y g of y is also absolutely integrable function. So, in such a case what happens, if this is the case, then all these things whatever you wrote as a double integral, this f x g y dx dy rather, to be more general, you can write f of x y as a two variable function, you can write, okay. For any fixed x, f of x y, fix x, f of x y is an absolutely integrable function from minus infinity to infinity. If you fix y, f of x y as a function of x is absolutely integrable function in minus infinity to infinity. So, then you can put this as f of x y, suppose this double it is the double integral of f of x y dx dy, modulus of that if it is less than finite, then what you get is modulus of f of x y. So, here instead of f of x y we have separately you take the product of f x and g y, okay. So, as a double integral, that means what is the meaning of integral? Integral means you take a finite interval. So, you the domain full plane minus infinity, the double integral dx dy means you have a full integral, full plane, full plane, each part you break it as a finite small rectangles, or each of that you calculate, you sum it, you take a sum, and then finally you take the limit. So, as that rectangle goes to 0, the area of the rectangle goes to 0, that is the meaning of double integral. You do not evaluate separately as a single integrals, okay. Suppose this is finite in general, and if the then the iterated integrals when they exist, they have to be finite, they have to be same, as double integrals. So, here also that is the case, this will be equal to the minus infinity to infinity. If it is this itself is finite, the iterated integrals will exist and they are finite. This is like f of x separately dx and g of y dy. So, these are separately, this I first evaluate and then I evaluate this one. So, this is same as minus infinity infinity minus infinity infinity. Instead, now what I have is g of y dy into fx mod fx dx. So, these are the two iterated integrals, they are also same. If double integral as double integral from the calculus, if it is a two variable function, a double integral is well defined. So, you should know that what is the meaning of double integrals, just like how you how you define a single integral as a area under the curve. So, here you view this double integral as a volume under a surface z equal to f of x y. So, f of x y is the function defined over some domain in the R2 in the plane. So, such a thing if you have, so double integral such a thing exists, what you have is the iterated integrals separately you evaluate, and those things should be same as this one. So, that is the Fibonacci theorem. So, here this fx and gy is our variables are separated. This need not be like this, you can choose the fx into gy as some let us say h of xy, which is a function of xy. So, h of xy, this statement you have to replace, if I choose instead of f and g, if you choose h of xy, you fix x, h of xy is absolutely integrable, you fix y, h of xy is absolutely integrable as a function of x in the full real line minus infinity infinity, and the double integral modulus of h of xy is finite. Then you can write these iterated integrals, these two will be same as this double integral. That is the meaning of this Fibonacci theorem. That is exactly what we use here. So, because of this, this is same as, you can now interchange order of integration, that is the meaning. Okay. So, if you change the order of integration, so that is the meaning of so because f and g now from this statement f and g both are absolutely integrable function. So, this is absolutely integrable functions f g. So, the double integral makes sense. Okay. So, this modulus of this is always less than or equal to this one, modulus of so this once you have this without the modulus f x g x g y dy, this modulus is less than or equal to this is double integral of this f x g y dx dy, which is finite anyway. So, this is also finite. So, you have this integral which is finite. So, you can do the order of integration by this Fibonacci theorem. We do not know whether we do that or not. So, we will see. We want to have separate we want to separate these x and y variables. So, what we do is, let us choose x minus y. I try to replace x minus y as a new variable. If I do this, let x minus y equal to t. If I use this, what happens to that integral? Get root 2 pi integral minus infinity infinity. So, inside, and you have x minus t, so that is I am integrating dy variable. So, dy x minus y is t. So, you have minus dy is dt. So, you have a minus dt. Okay. And when you put y equal to minus infinity, it is going to be x minus infinity is a plus x minus y is minus infinity, plus plus infinity to minus infinity. So, if I remove this minus and make this interchange these limits, this will be this, and what you get is f of t into modulus of this, and not modulus, without modulus, right. So, we are looking at this integral. So, this one g of y, g of y is so g of y, what should I do? G of y is I forgot, wait. 20 minutes. 20 minutes. So, I think so this up to here a little bit is okay. So, because of this Fibonacci theorem, we can do the order of integration. I think that is required. So, that is equal to 1 by root 2 pi, I will just do the order of integration because of the Fibonacci theorem. So, minus infinity. So, this iterated integral, instead of doing this way, I get x minus y g of y e power minus I xi x. Earlier I have dy by dx, dy into dx. Now, I do first dx and then dy. Okay. Now, we look at this 1 by root 2 pi minus infinity infinity inside the dx part, that is f of x minus y e power minus I xi x dx into g of y dy. Now, you look at this one, here you try to use x minus y equal to t. If you do that, this is the dx will be dt, and you have then the double integral becomes 2 pi, inner integral becomes this is limits as any minus infinity minus y, y is fixed. So, that is minus infinity plus infinity minus fixed y is actually infinity. So, limits will not be changing, you have f of t and e power minus I xi x becomes y plus t, and you have dx is dt and g of y dy. Now, they are separated, variables are separated now, 2 pi minus infinity to infinity minus infinity to infinity. Now, you write f of t e power minus I xi t dt separate, and then into g of y, this you write e power minus I xi y dy. This is nothing to do with y, so that it is a constant that comes out, and with 1 by root 2 pi, that is exactly f cap of xi into minus infinity infinity g of y e power minus I xi y dy. This is root 2 pi, I need 1 by root 2 pi into, I have to multiply 1 by root 2 pi. Okay. So, this is actually g cap of xi. So, f cap of xi into g cap of xi. This is exactly my f star g, that is a convolution product of f convolution product Fourier transform of that as a function of xi is actually this. This is exactly what we want to prove as a property. This is right. Okay. So, if I define, if you do not want this part, if you do not want this this thing, you can redefine your convolution product as 1 by root 2 pi. If you do this, then there won't be any there won't be finally any root 2 pi in the final property. Okay. You will not get this one. So, let us not define. So, let me stick to what I mean. But you do not multiply anything, simply take the as usual, simply take the product of the two functions, and one with x minus y, other one is g of y. You integrate it, that is the convolution product, then what you get is this result. So, Fourier transform of the convolution is actually with some constant root 2 pi times Fourier product of Fourier transforms of f and g. One more property that is basically corollary of this byproduct of this property 9 is Parseval's inequality, Parseval's equality, Parseval's identity. You can get nice identity, that is that tells you that double integral of absolute square of this let us say f x modulus square dx is same as this one. So, f cap of xi square d xi. This is what is true if f of x is absolutely integrable function. Okay. So, if such a thing, you have this nice identity. So, this in physical problems is more generally energy is represented as a square integrable as a square integrable function. So, that is why is this identity tells you some kind of energy conservation. Okay. So, you have this Parseval identity. Let us prove mathematically what it is. So, it is the byproduct of this earlier property, and from the earlier property you can easily see that you just write the earlier property, you get what you want. This is exactly root 2 pi f cap of xi into g cap of xi. Now, what you do is you take the inverse transform of this. If I take the inverse transform of this, let me write inverse transform like this of f star g cap of x. If you do this as a function of xi for this, then what you get is finally function of x. Okay. So, this is root 2 pi inverse transform. Inverse transform is I will just write 1 by root 2 pi minus infinity for this f cap of xi g cap of xi into e power I xi x d xi. This is also function of x. So, this gets cancelled, and here this is exactly, this is nothing but f star g of x, which is equal to minus infinity f cap of xi into g cap of xi e power I xi x d xi. Okay. Now, what you have to do? Simply put x equal to 0 here. So, what exactly this means? This means in my definition of convolution product, I do not have any constant multiplication constant. So, you simply define as this way f of x minus y g of y dy. So, if I choose like this, put x equal to 0 and choose g of y as remember in the property, earlier property, f and g both are absolutely integrable functions. So, g of y you can choose as a function of how do I choose this function of once I choose this is x equal to 0. Once you choose x equal to 0, let us see what happens. So, x equal to 0, what you get is minus infinity f of minus y g of y dy, which is equal to minus infinity f cap of xi g cap of xi d xi. Now, what you do is you choose so this is same as minus infinity to f minus y, you replace it as y, that means you take minus y equal to t for example. So, then you have f of t then g of minus t dt, dt is minus dt, and you have this will be, this becomes infinity to minus infinity, that makes it minus infinity. So, both are same and you get this one f cap of xi g cap of xi d xi. So, what I choose is I choose g of minus t as f of t bar. If I can choose this, if f is a complex valued function, f is a real valued function, or which is also you can think of complex valued functions, right. So, this modulus square means this square means f x into f x modulus square in complex, if you can think of even complex, real number is also complex number, right. So, f x, even if it is a real valued function, you can think of, you have seen that signals can be even complex valued function. So, f x is actually can be a complex valued function. So, f x bar modulus of f x square is f x into conjugate of f x. So, in that way, if f is a absolutely integrable function, f dash of f bar conjugate of f is also absolutely integrable function. So, you can choose such a some g in such a way that which is g of minus t as modulus of this, if you choose, then g of minus t is also absolutely integrable function. Okay. Then g of t is absolutely integrable function, then what you see is this identity becomes minus infinity to infinity modulus of f of t bar square dt, that is exactly your left hand side and the right hand side. So, once you have this, what is your g cap of xi? G cap of xi so what is this g cap of xi? So, this we try to use, so we will try to see this one separately, f of xi, and here g of xi is, so what you have to replace, what happens to this g cap if I calculate g cap of minus t, what is this one? This is equal to g cap of minus t if I multiply, if I take the Fourier transform, which is a function of xi, which is 1 by root 2 pi minus infinity to infinity g of minus t e power minus I xi t dt. Okay. Then so what is g of t? 1 by root 2 pi. Now you can put just the g of minus t as f of t bar e power minus I xi t dt. So you can do 2 times conjugate and you allow that 1 inside. So you have a bar 1 by root 2 pi minus infinity to infinity. If you take this bar for this is a complex number. So, as it is, limits are complex numbers. So, real numbers. So, bar conjugation does not matter, and this becomes f of t and this becomes e power I xi t. So, this is become plus t, right, dt is a real number. So, this is what you get. So, this is actually equal to a bar of, and this you can write minus of minus xi. Okay. So, that makes it bar of f cap of minus xi. Okay. So, what you got is g cap of minus t, if you take, this is what you get. So, if you take what you need, if you take, so this implies you get g cap of, so g cap of minus t, which is a function of xi. This is what you get. This means g cap of xi is what? This is g cap of or you start with g of t is f of minus t, let us say. Okay. G of t is, once you choose like this, first of all, once you choose like this, then what you get is g of t equal to f of minus t bar. So, g of t, so if I replace t, then you try to calculate only g t, okay, then only g t, this is what happens, and f of minus t I have to put, right. So, what you get is f of minus t, and this is what you get. And then you do the change of variable here. So, here if you try to do the change of variable, t equal to minus t equal to x, if you do again, what you get is bar of 1 by root 2 pi minus infinity, that becomes plus infinity to minus infinity f of x e power minus I that is anyway I xi t. So, minus I xi x dx is minus dx. So, that makes it minus infinity to plus infinity. Okay. So, with bar. So, this is exactly equal to f cap of xi. bar. So, if I choose this, g of t is this. So, f cap of g bar is, so this is exactly my g cap of xi. So, this means g cap of xi, which is a function of t, for which if you take the Fourier transform, which is a function of zeta, it is a transform variable. So, you have a g hat of xi is f hat of xi bar if your g or f are related by this, which is same as this. Okay. So, in that way, if I now becomes, so what do I have to, I can replace g cap of xi with f cap of xi with conjugate d xi. So, this is exactly minus infinity infinity absolute value square f cap of xi square d xi. So, this is exactly what you want, f x, let us write dx. So, this is the Parseval's identity. So, which is making a conservation of energy kind of thing, because the square integrable function normally energy is represented like in this integral representation, square absolute value of the square integration in general. So, most of the physical problems if you see energy is represented this way. So, you can think of this as a conservation of energy before transformation and after transformation. Okay. So, this is one property, important property, and one more we will do. So, that with that we will try to prove the Fourier integral theorem. We will look at the property, it is called Riemann-Lebesgue lemma, Riemann-Lebesgue lemma. We have already seen this for piecewise, we have seen this Riemann-Lebesgue lemma for periodic signals, that is if you have a signal of defined for x belongs to minus L by 2 to L by 2. So, what you have these Fourier coefficients goes to 0 as mod n goes to infinity. So, this is exactly, this is the finite that is a Fourier series version of Riemann-Lebesgue lemma. So, in this case what is this one? So, what we do is now we want to do for non-periodic signal, that is f x is defined over full real line. If such a function f x is a signal, f x is and it is, you assume that is absolutely integrable and piecewise continuous. You have only finitely many discontinuities in minus r to r, minus infinity to infinity. So, such a function if you have, then what you have is limit the Fourier transform of this mod xi goes to infinity is actually equal to 0. So, look at the proof. So, what we do is we try to take this f cap of xi, we apply this limit. So, we will try to apply. So, what is this meaning? That is as a limit definition if you use, this is f cap of xi, this is less than epsilon whenever mod xi is bigger than k, some big let us say some k which is positive for some k belongs to a real number. So, if such a thing happens, so this means this is always true given epsilon positive, that is, so you can write like this, for given epsilon positive we have this thing. This if you have this for some always k, then you say that this limit is equal to 0, that is what we are going to show. So, we are going to show this one. So, for that you write Fourier transform, which is by definition 1 by root 2 pi minus infinity infinity f x e power minus I xi x dx. So, for this you take the modulus, what you want is this one. So, you take the modulus. So, now we have the modulus, and this one is you split this into two parts. This integral you can split this into two parts. So, what I do is 1 by root 2 pi This is from minus infinity to some number, some big number a minus a f x e power minus I xi x dx plus a to infinity same f x e power minus I xi x dx, and then plus 1 by, of course 1 by root 2 pi you have 1 by root 2 pi. Now, what is left is minus a to a f x e power minus I xi x. So, I split this integral into 3 parts. So, this is less than or equal to 1 by root 2 pi integral minus infinity to infinity mod f x. I take this modulus inside. So, this whole integral, say this whole integral modulus, which is again less than or equal to, I can take this modulus inside this integrand, that is mod f x into e power minus I xi x, that is actually mod f x dx. This is to minus a plus a to infinity mod f x dx. So, this is one part, and the other part is plus 1 by root 2 pi minus a to a. So, let me write here minus a to a f x e power minus I xi x dx with modulus. So, we look at this one. So, this is how if I have to show that this part and this part together, they are like they can be made less than epsilon. So, we will look at that one. So, because f is absolutely integrable function, and what you have is the integral, this means minus infinity to infinity, because it is minus infinity to infinity mod f x dx is finite, that is the meaning. Okay. So, what is this meaning of this one? This is actually equal to, so limit of a goes to infinity for some a minus a to a f x mod f x rather. Okay. This is the meaning of this improper integral. So, this is some number, this is the limit. So, what does it mean? So, this means this minus this. So, that is the with modulus. So, a modulus of that is actually this one. So, minus infinity to infinity minus infinity to minus a mod f x dx plus a to infinity mod f x dx. This quantity can be made less than epsilon whenever, so given epsilon positive. So, you give epsilon any however small it is, you give such an epsilon, I can make this quantity less than epsilon whenever for some a big enough, for some big a belongs to a. So, for a is, so let us say a bigger than some k 1, okay. For a bigger than k, so you say like this, for or rather this can be made less than if a is bigger than k 1 for some k 1 belongs to the real numbers. So, technically this is the meaning of this limit, this is the definition. Now, you want to show this one. So, what happens to this? For this, now this means f is defined over interval minus a to a. So, this is exactly what we do. We try to use we try to take this function as a periodic signal defined over minus a to a. Okay. So, once you have this, you have a Fourier transform. So, what we have from Riemann-Lebesgue lemma for this periodic signal is f cap. So, you have Fourier transform of this over a finite interval, they are nothing but Fourier coefficients Cn mod n goes to infinity, this is 0. So, what is Cn? Cn is limit n goes to mod n goes to infinity, the Cn is nothing but 1 by 2a integral minus a to a f x e power minus I n omega naught is 2 pi by, this difference is 2a. So, pi by a x dx. So, these are your Cn, which is actually 0, as this is the meaning of Fourier Riemann-Lebesgue lemma. lemma for periodic signals. Periodic signals, that means any function signal over a finite interval. So, this is what we have. So what does it mean? So, but then this tells you that what you need is integral minus minus a to a fx into e power minus I xi x. So, I xi is this one here. So, this is your xi. Xi is a continuous variable. So, if you actually see, xi is a continuous variable. So, this tells you that n pi a, as n goes to infinity, pi by a, once you have fixed a, n pi by a is n equal to 1 pi by a. So, that is a positive number, some number, and then n equal to 2, it will be having like this, it will go to infinity. That is how the sequence of sequence n pi by a. N pi by a sequence goes to infinity as n goes to infinity, as like this, right. This is the meaning of going to infinity, but what you need is xi goes to infinity. So, what you require, what you look for is xi goes to infinity. So, that means if my sequence is here going to infinity like this, that also should be accounted for. So, what I do is I consider a plus some small interval. So, let us choose some small interval, let us say 0 to 1 interval. So, if you add, so what you get is a plus 1 minus a plus 1, and you just add, a you take bigger than this, a you take a for this a, once you fix a. So, such a big a you try to consider a plus 1, okay, instead of a you consider a plus 1. Okay. So, if I do that, still even if I, so this means if a is this, if I choose, if I take a plus 1 here, so if I take a plus 1 here, still this is valid, because a plus 1 is bigger than still k1. So, then that way, so this is, I can choose some b as a plus, now some you can say open intervals or closed interval, does not matter. Okay. So, you can choose the interval b is like this, okay, a plus some x, x belongs to this closed interval, let us say. So, then you can replace this with b. Okay. So, any b, that is still valid. If b is this, then still I have that quantity. So, that minus infinity to minus a, okay, minus b mod f x dx plus b to infinity mod f x dx is still less than epsilon if b is bigger than some k1 for some k1 belongs to R. So, that means same k1 will work for every b if k1 is you choose k1 as a plus 1. So, I try to choose a plus 1 as here. Okay. If I choose a plus 1, this is what is true. Okay. So, both are same, right. So, a goes to infinity. So, let us choose like this. Okay. This means this minus this, as a goes to infinity, a plus 1 is also, I am just replacing a by a plus 1, that is all, otherwise everything is same. A plus 1 goes to infinity is same as a is going to infinity, both are same. Okay. So, that means this is true. So, for a plus 1 when you choose, you have such a k1 exists. Now, if I choose b as a plus x, x belongs to 0 to 1. So, if we start with a plus small 0.5, a plus any number in between these real numbers, okay, this interval anything you choose. So, this is still valid for the same k1. Okay. And then you look at every time, so you already have this a plus 1, right. Now, you have instead of a, you have a plus 1 interval, and you have everything a plus 1, this is what exactly you have right now. Okay. A plus 1. So, this is exactly your z. Okay. So, if you choose this one, a becomes a plus 1. So, this is the Riemann-Lebesgue lemma for this interval. So, you have some sequence. Now, if you choose b, that is a plus, you try to choose some interval in between this this interval. Okay. So, if I choose this interval as let us say b minus b to b, okay, this is actually contained in this, if I choose b like this, okay, it may be same if I choose x equal to 1 here. So, you do not want to call x, call this some y, okay. If my y equal to 1, this is exactly minus a plus 1 to a plus 1. So, in this case what happens is that every time you change this one and you a plus 1 becomes b. So, 1 by 2 by b. So, you have n pi by b. So, as you choose your y variable here in this interval, so you will see that every time the sequence is, it covers all sequence. Once you choose different thing, it will have a sequence that goes to infinity as n goes to infinity, okay. So, this implies n pi by b, this sequence going to infinity as n goes to infinity, okay. So, this is always true. So, what is the definition for this is the Riemann-Lebesgue lemma definition is 1 by 2 times a plus 1 is 2 minus a plus 1 to a plus 1, okay. So, if I write like this, f x e power minus I n pi by a plus 1 x dx. This quantity can be made less than epsilon whenever if n is bigger than, or right, n is bigger than some big number, for some n belongs to the natural numbers, some big number n. Now, if I choose minus b to b, this is the same n number will work, but it is the different sequence that converges to infinity, okay. So, if I choose, so so every time you do that, what you get is this quantity is still true. So, that way if I choose like this, the same n which is valid from minus a plus 1 to a plus 1 interval, this Riemann-Lebesgue lemma, when you choose this one, it is still valid. So, this quantity is always less than epsilon whenever if I replace this by some xi, if I try to put it as xi, and then this you can keep it as the same, okay, then it is still valid. So, this is this can be made less than epsilon for every n bigger than this, yeah, n is not there. So, now instead of n pi by b or n pi by a plus 1, I replace with xi. So, I replace this n as n pi by a plus 1, I can replace with some xi both sides. So, mod n goes to infinity, this goes to infinity, or mod n goes to mod n into that, okay. So, whichever way. So, even the negative side you have the same sequence, you have a sequence that converges to minus infinity. That way also you can look at it in that way. I can choose mod xi bigger than n for some n. So, you can call this, instead of this n, you call this some k2, okay, which is positive for some k2, you call this. Then if you combine these two, this one and this one, if you combine and put it here, so this quantity is less than epsilon. So, instead of a you have a plus 1, so it does not matter. So, you can write this is a, you replace with a plus 1, or a plus 1 you replace finally a, okay. So, it does not matter, this is epsilon already, epsilon by root 2 pi, and this one is 1 by root 2 pi. This quantity is 2 times, where is this one? So, this is 2 times a epsilon, okay, 2 times a plus 1, right, 2 times 1 by 2 a plus, yeah, that is it. So, into epsilon. So, this is what exactly. So, this is a fixed quantity times epsilon, this is a fixed number, finite number into epsilon. So, that means what you have proved is some fixed number, let us say some L into epsilon. So, where L is a finite number, finite real number. So, that means mod f of this modulus of this quantity I could make less than epsilon. So, where is this valid? When you have this quantity is less than epsilon, and this quantity is less than epsilon. So, that means it is valid for every mod xi is bigger than for every mod xi bigger than some k2, okay, and also k1. So, k1 is k1 k2 whichever is bigger you pick up, okay. So, k1 k2, so you pick up k which is a maximum of k1 and k2. So, if I choose like this is exactly what I want to prove. So, k is such a thing. So, that means this limit is actually 0. So, this is how you can prove this Riemann-Lebesgue lemma. We can also prove this Riemann-Lebesgue lemma. We can also prove this Riemann-Lebesgue lemma by some other way. We will try to prove that prove that in the next video, and we will also prove finally eventually we will later on once we prove this by other method, we will also prove finally Fourier integral theorem, which is what is the requirement for us to believe that the definition of a Fourier transform and its inverse transform. Thank you very much. We will see in the next video.